Okay, before we move on to solving an example or structure, before solving a structural stress dynamic problem, let's quickly try to get familiarized with the natural frequencies of a one-dimensional bar, or the concepts behind how to calculate natural frequencies for one-dimensional bar. So 10.3, let's calculate natural frequencies of a one-dimensional bar. Okay, we will first describe how to determine the natural frequencies of continuous elements, and specifically in this case, we will be focusing on bar element. And we know the natural frequencies are quite important, and they are necessary in vibration analysis, and also important to choose proper time step for structural dynamics analysis. So we need to select a time step such that we capture all the proper dynamics when it comes to analyzing complicated structure. So we know natural frequencies are can be determined by solving this equation, which we already derived. So the time dependent force applied on the system, the contributions from the internal forces, and the contributions from the dynamics of the system dynamics, so to say, right? So we need to solve this equation in order to access the natural frequencies. So in the absence of this external force, we can represent this equation in the matrix using the matrix notation, where we have to deal with the mass matrix times the acceleration terms and the displacement matrix multiplied by the stiffness matrix. And in the absence of external absence of forcing function, that is Ft, we end up with this equation, right? So the standard notation for, let's say, dt for an harmonic equation in time can be represented using this function, where dt kinds of acts as an amplitude raised e to the power I omega t. I think you are quite familiar with this notation. This is a solution, standard solution for a function representing a harmonic equation in time. Here, d dash t is kind of like part of the nodal displacement matrix. Yeah, part of nodal displacement matrix. Also called natural modes. We call it natural modes. So these natural modes are assumed to be independent of time. Okay, so I is the standard imaginary number, where I is equal to the square root of -1, and omega is of course the natural frequency. So we can differentiate this equation twice with respect to time to obtain the following equation. So we obtain the acceleration d double dot is equal to t dash minus omega squared, now ei omega t. So in the next step, we can use this solution in equation 10.3.2 and 10.3.1. So to rewrite it, to obtain, so what we will be using is, we will be using this notation, the equation for dt and d double dot t, of course, in the original equation, that is equation 10.3.1. Once we do the substitution, we will get minus m omega squared d dash ei omega t plus k, instead of, we can write d dash ei omega t is equal to 0. So we can combine the terms in equation, let's say 10.3.4, to obtain ei omega t k minus omega squared m d dash is equal to 0. We know that ei omega t is obviously not 0. So then, in order for this function to be 0, the following condition has to be satisfied. So we know this equation is a set of linear homogeneous equations in terms of displacement mode d dash. So because the equation 10.3.6, the one we just wrote, has a non-trivial solution if and only if the determinant of the coefficient matrix of d dash is 0. So that we have, so the solution for this equation is the determinant of the coefficient matrix of D has to be 0 in order for this function to be 0. So we know this equation represents an n number of algebraic equations, where n refers to the number of degrees of freedoms associated with the problem. So in order to illustrate this procedure and to get familiarized with the natural frequencies, let's try to solve a simple problem. Well, let's try to tackle the following example. Let's call it example 10.1. Or let's call it, to be specific, 10.3. Okay. So let's consider a bar element, one-dimensional bar, which we would like to extract the natural frequency. Simple one-dimensional bar has a length of 2L. Local coordinate system is X. And for this bar shown in this figure, the modulus of elasticity is E, and the mass density, corresponding mass density of the material is rho. Cross-sectional area of the bar is A, and we are supposed to determine the first two natural frequencies. All right. So for simplicity, the bar can be discretized into, let's say, two elements, each having a length of L. We can discretize this bar in the following formation. Into two elements. This is the first element and the second element, each having a length of L. So in order to solve this equation represented by 10.3.7, which gives access to, let's say, the natural frequency modes or the natural frequencies, we must develop the total stiffness matrix for the bar. Yeah, because we see that the K value enters into the equation. So we need to develop this total stiffness for the bar. For this, we can either use the lump mass matrix or the consistent mass matrix approach. So in general, we know that using the consistent mass matrix, the result seems to be more accurate to the ones obtained from the analytical or experimental results than those found using the lump mass matrix method. But for the longhand calculations, it is quite tedious to use the consistent mass matrix than using the lump mass matrix, because the consistent mass matrix is a full symmetric matrix, whereas the lump mass matrix has a non-zero terms only along the main diagonal, which makes us easy and convenient for do a hand calculation. So for simplicity, let's use the lump mass matrix for this to perform the calculation. And the first step is to use write down the stiffness matrix for each element. Yeah. We have two elements. Let's write down the stiffness matrix for each element. So for element 1, the stiffness matrix is A divided by L. Then the corresponding nodes are 1, 2, 2, minus 1, minus 1. And if we consider element number 2, the corresponding nodes are 2, 3. So using the direct stiffness method, we can assemble the element stiffness matrices to obtain the global stiffness matrix for the whole bar. So the global stiffness matrix for the whole bar can be obtained using K is equal to AE over L. Once you do the summation or do the superpositioning using the direct stiffness method, you can simply adapt the corresponding terms in the two element stiffness matrices, and you would end up in getting this result. So then our next step is to obtain the mass matrices for each element. Yeah, we know we have two elements. The mass matrix for the first element, we are using the lumped mass matrix method. So it is rho AL, total mass, divided by 2. The total mass is simply divided into the two nodes equally. And similarly, we have the mass matrix using the lump mass matrix method for the second node. So the mass matrices for each element are then assembled in the same manner which is done for the stiffness matrices. So what we now let's try to obtain the global mass matrix. Global mass matrix M corresponds to rho AL divided by 2 in the same way that we have added up the element stiffness matrices. We are now adding up the mass element stiffness matrices to obtain the global mass matrix. So we observe from the global mass matrix that there are two mass contributions at node number 2, because node number 2 is common to both elements. So one half gets added, each half gets added by each element. So now we can substitute the global stiffness matrix and the global mass matrix into the main equation, and also apply the boundary conditions to reduce a set of equations, and we can obtain the results the usual manner. We know we are dealing with a fixed end, so we know the displacement at node number 1 is 0. So we can simply eliminate that row, and if we consider the reduced set of equations, and by substituting the values which we obtained into this original equation, which we like to determine here, yeah, and simply considering this boundary condition, we can obtain the reduced set of equations in the following way. K matrix, which is 2 minus 1 minus 1 1. This is only the sub matrix now of the total matrix, because the ones corresponding to D1 x hat has been eliminated because they're 0. This is the mass matrix 2 0 0 1 times D2 dash D3 dash is equal to 0. All right. In order to, let's say, obtain a solution for this set of equations, we set the determinant of the coefficient matrix equal to 0, as indicated previously, as indicated in this equation. So we set the determinant of this equation, of this part here, to be 0. So we can set AE divided by L 2 minus 1 minus 1 1 lambda. Let's introduce a new term to take away the omega squared term, rho AL 2 2 0 0 1. So here lambda corresponds to omega squared, and by dividing the equation rho AL, we simply write it down so that you won't get confused. By dividing it by rho AL, and of course letting this term mu to be E divided by rho L squared B equal to mu, we obtain the following formation or following notation. You can try it on your own. I will simply write down this equation here just to save time. Mu minus lambda divided by 2. Okay, so for evaluating this determinant, what we obtain is lambda is equal to 2 mu plus or minus mu square root of 2. Or in other words, lambda 1, we have two solutions, is equal to 0.6 mu, and lambda 2 is equal to 3.4541 mu. So just for comparison, just for comparison with this is the results we obtained for lump mass matrix. For comparison with the exact solution, the lambda is given by 0.616 mu, whereas the consistent mass approach provides a value 0.648 times mu. So it is clear that for bar elements, sometimes specifically for bar elements, the lump mass approach can provide results as good as the consistent mass matrix approach. Sometimes even better. Right. Now, having said that, we are mainly interested in calculating the first and the second natural frequencies. Since we have calculated the lambda values, it's all about calculating now the omega. So omega 1 is equal to square root of lambda 1, which is 0.77 mu square root of mu, and omega 2 is equal to square root of lambda 2, that is 1.85 square root of mu. So if we assume the modulus of elasticity to be 3 times 10 to the power 6 pounds per square inch, and the mass density rho is equal to pounds per second square inch time quadratic L is equal to 100 inches, we can obtain mu, since it is E divided by rho L squared, 30 times 10 to the power 6 divided by 0.00073 times 100 squared. See, 4.12 10 to the power 6 per second. So the natural frequencies are then in the range of omega 1 is equal to 1.56 times 10 to the power 3 radians per second, and omega 2 is equal to 3.76 times 10 to the power 3 radians per second. So in hertz, we know it's omega 1 divided by 2 phi. So it's 248 hertz. Yeah. So what can we get from these results in conclusion? What we have done is, for this particular discretized bar, such that the two nodes are free to displace, there are two natural modes and frequencies. So when the system vibrates with the natural frequency omega I, that unique shape with an arbitrary amplitude corresponding to omega I is called the mode of vibration. In general, we know for an n degrees of freedom, which has been discretized, there are n natural modes and frequencies. So a continuous system actually has an infinite number of natural modes and frequencies. So however, when the system is discretized, let's say to n number of segments, only n degrees of freedoms are created, and the lowest modes and the frequencies are approximated most of the time when we perform calculation, and the higher frequencies are mostly damped out and rapidly damped out more rapidly and used for less, and they are of less importance. So what lies in the low frequency range are considered to be important. So a rule of thumb is to use 2 times as many elements as the number of frequencies desired when if we want to calculate, let's say, natural frequencies of a let's say a bar. So since we already have, let's say, since we already have access to lambda 1, then we can readily find out the vibration patterns or the displacements of the first mode and the second mode itself by solving the simultaneous set of equations, since we already have access to the natural frequencies, which I will not detail in this section, and it is up to you to maybe read and get familiarized how you can do that, because it's simply a substitution and obtain and observing, let's say, the modes, the first and second modes of, let's say, longitudinal vibration, in this case for a cantilever bar. So this is something up to you to do. And yes, by now I think you have a quite sound understanding about how dynamics or time dependent analysis can be performed for a finite element, simple finite element formulated problem. We have already applied it to a bar and how to calculate natural frequencies for a particular bar. It is the same protocol or the same procedure when you apply also to a beam. It's just the fundamental equations change based on the type of element, but the procedure is the same, because when we move from a bar to a beam, there are additional number of degrees of freedom, and the corresponding, let's say, the stiffness matrix will vary based on the number of elements you use. The global mass matrix will vary, and if you follow the same procedure and apply the concepts that you used here, you will it is the same steps that you have to go through when you're analyzing even, say, more complicated, or let's say more elements having large number of degrees of freedom. So I will not do more examples which has large number of degrees of freedom, but I will post some worked out examples for you to go through and get familiarized with this section. On that note, I would like to wind up the section on structural dynamics and, of course, time-dependent problems. Thank you.